So let's take a look at what's happened in the past 40 million years, because on the one hand, you can look at 40 million years ago and say, well, that's a long time ago. It doesn't have very much to do with the future. But I'll show you explicitly exactly why that's not the case, why what happened 40 million years ago tells us exactly where we're going in the next very few decades. So let's start with this diagram that begins 40 million years ago and moves forward in time to the present. That's the horizontal axis, moving from right to left. The vertical axis on the right-hand side is the temperature in degrees Celsius, and it's pinned to 0, which is the current average surface temperature of the Earth. That is, the global average surface temperature of the Earth. On the other axis, it plots the concentration of carbon dioxide in the atmosphere from 250 to 850 parts per million. And it tracks this remarkable relationship between global average temperature and the carbon dioxide concentration. And as we'll see in a moment, it's the carbon silicate chemistry that draws carbon dioxide out of the atmosphere on the time scale of tens of millions of years. And so when we look at the condition 40 million years ago, the average surface temperature was some 8 Celsius or 8 Kelvin above the current level, and the carbon dioxide concentration was about 850 parts per million. Now, remarkably, and this is captured in the Museum of Natural History in Washington, D.C., there's a picture based on fossil fuels of what the Arctic Ocean looked like 40 million years ago. And 40 million years ago, these tropical beasts and plants existed year-round in the Arctic. That meant that the temperature of the Arctic never even approached the freezing point, because these species are killed within a month by temperatures of that magnitude. So year-round, the Arctic was very warm. In fact, there's evidence to say that there was a very small temperature difference between the equator and the polar regions. So it was a very, very different climate. Also, severe storms, hurricanes, and so on were far more intense because, as we learned from thermodynamics, the energy contained in water vapor is tremendous, and the conversion of that vapor to liquid phase in a storm system releases massive amounts of energy. So the frequency and intensity of severe storms globally was dramatically greater than it is today. Moving from the Eocene 40 million years ago to the present, the chemistry that's at work involves the carbon dioxide that's intrinsic to the atmosphere that's absorbed by rainwater. And one of the great things about acid-base chemistry is that we can calculate exactly what the acid content of that rain is, the pH, the concentration of H plus in water. But when that acidic rain falls on calcium silicate, it flows from the river systems into the ocean, and it converts that calcium silicate to the bicarb anion and the calcium cation and silicon dioxide. That's sand, basically. But that calcium cation reacts with the bicarb in the carbon chemistry to produce calcium carbonate. And that calcium carbonate sinks to the bottom of the ocean, and that's what created the massive deposits of sandstone or limestone globally. And that's what drew inexorably the carbon dioxide out of the atmosphere over these tens of millions of years. And it drew the concentration down to about 200 to 250 parts per million. And as soon as the carbon dioxide concentration gets that low, the oscillation between ice ages and non-ice ages, that's glacial to interglacial, is a function of the details of the orbit of the Earth. But as soon as the carbon dioxide concentration gets up to 300, 350 parts per million, the trapping by infrared radiation completely swamps the signal generated by the orbital parameters of the Earth. So when we stand back and look 40 million years into the past, it's tempting to say, well, that's 40 million years ago. I'm interested in what's happening next year, 5 years from now, 20 years from now. So to demonstrate that, let's plot the change in temperature from the present day exactly the same way we did before. 0 is a condition equal to the current average temperature of the surface of the Earth. And on the other axis, we'll plot the carbon dioxide mixing ratio. Now this is the effective carbon dioxide mixing ratio. In the evolution from the Eocene to 2 million years ago, the carbon in the atmosphere was dominated by CO2. There was very little methane, very little N2O, very small concentrations of chlorofluorocarbons in the form of chlorine and bromine. So when we hit the point 2 million years ago, the glacial interglacial was controlled by the orbital parameters. But as we began to add carbon dioxide to the atmosphere, we turned the corner and began evolving back up along the same parallel leg, except now this is with increasing carbon dioxide. And interestingly enough, we know that there's 400 parts per million of CO2 in the atmosphere because we just passed that point. But when we count the increase in methane, the increase in N2O, and chlorofluorocarbons, we're actually at 500 parts per million of effective carbon dioxide. That was what was present 10 million years ago. But we're adding carbon dioxide and methane so rapidly to the atmosphere that by the end of the century we'll be somewhere between 800 and 900 parts per million. That's going back 25 to 30 million years ago. And even 10 million years ago, there was virtually no ice in the northern hemisphere. All of these ice structures are unstable above 300 parts per million. So this carbon chemistry turns out to control not only the acid-base character of the system, but also the trapping of infrared radiation. So just to make sure that this point is clear, we're looking at the end of the century at carbon dioxide effectively being between 800 and 1,000 parts per million, and that puts us back between 30 and 40 million years ago in the clock of carbon dioxide versus temperature. And to think that it took 40 million years to go from the Eocene to 2 million years ago, and it's taking just a little over 100 years to go all the way back up that curve in CO2 temperature space, is a shocking reminder at how quickly the onset of climate change induced by the combustion of fossil fuels is upon us.